Okay, now let's see if we can work out an expression for the line intensities. That is, how strong is the absorption at each absorption line in our spectrum relative to the others. So hold on for 1 second here. Okay, let's suppose we're looking at a particular transition from some state with rotational quantum number j to some final state with rotational quantum number j prime. Okay? So the simple idea that we'll use is that the line intensity should be proportional to the probability of occupancy of the state J, of the initial state, okay? Because we can only have a transition if there's a molecule in the initial state waiting to be promoted to the excited state, okay? Now, what's this probability of occupancy? Well, that's going to be proportional to the degeneracy of the state, the number of states for this molecule that have that value of J, okay, times the probability of occupancy for each of those states. So how many of these, on average, are actually occupied? And of course, we can only have a transition from an occupied state up to the excited state. Now, the degeneracy turns out to be 2j plus 1. Okay, where does that come from? This is the number of, remember, j only specifies the magnitude of the angular momentum. To fully specify the angular momentum, we also have to know its z component, which is specified by the magnetic quantum number. And for every value of j, there are 2j plus 1 different distinct magnetic quantum number values. So that's where that's coming from. Finally, we have to multiply this by the probability of occupancy of each of these states, which is given by a Boltzmann factor, e to the minus the energy of the state divided by kT, okay? This Boltzmann factor comes from statistical mechanics. It might be familiar to you, but we can't derive it here. We're just going to use it, okay, as a pre-made result. Now, if you're thinking very carefully, you might also imagine that the intensity should depend on how many unoccupied states there are in the excited state, because in order to have a transition, the molecule has to go into a previously unoccupied excited state level, okay? And that's right, but there are two things here that simplify it for us. First of all, for every initial state, every transition from a particular initial state, a particular value of J and a particular value of the magnetic quantum number, there's only one final state that the transition can go to. So in essence, the number of possible final states is always 1. And then second, the energy of this state is so high for the rotor vibrational transitions that we can assume that it's going to be unoccupied, because essentially no molecules, only a vanishing fraction of molecules, have enough thermal energy to be found in this state with any probability. Okay, very good. Let's just finish this up. So the absorption intensity is given by this expression here, where E sub j is the energy of the lower state. So it's j times j plus 1 times B0. Okay? You have to be a little careful with this expression, though, because notice we're using j and j prime to denote the initial and final states, and that's not how we used those terms earlier in our discussion. So in particular, for the R branch lines, we have to realize that what we've been calling j, that's the quantum number in the initial state, is the same thing as m minus 1, where m is the line number. And on the other hand, for the P branch lines, what we're calling J is equal to the absolute value of M, because M is negative for the P branch lines. Anyway, with those changes, you can use this expression to find the intensities, okay?